If it changed course and at roughly the same speed, not making it much faster, then it would take a couple of months or so, a few months, depending on exactly the details.
At first glance, the trajectory looked ordinary enough. Hyperbolic? Yes, but that alone wasn't shocking anymore. Interstellar objects are expected to move fast, to cut through the solar system on paths that don't loop back. Once you accept that visitors from other star systems exist, a strange orbit stops being strange. It becomes a checkbox. And for a brief moment, that's what scientists hoped 3I Atlas would be. Another box to tick, another line added to a growing but manageable category. Then they tried to reconstruct where it came from. Trajectory analysis is supposed to be the easy part. You measure position over time, factor in gravitational influences, and run the math backward. Most of the uncertainty washes out as observations pile up. The object's past narrows from a cloud of possibilities into a thin corridor through space. That corridor tells a story: what star system it might have passed, what forces shaped its path, how long it wandered before stumbling into ours. With 3I Atlas, that corridor refused to form. Instead of tightening, the solutions spread. Different models produce different answers, not by a little, but by enough to matter. Small changes in assumptions, solar radiation pressure, mass estimates, rotational state, sent the reconstructed path drifting in wildly different directions. It was like trying to trace footprints backward through sand while the wind kept changing direction. At first, the explanation was obvious: insufficient data. Early observations are always rough. You don't overreact to preliminary fits, so teams waited. More measurements came in, the timeline extended. The positional accuracy improved. The problem didn't go away. What made this unsettling wasn't that the trajectory was unknown. Plenty of objects have poorly constrained pasts. The issue was that even with better data, the uncertainty refused to collapse the way experience said it should. Instead of converging on one dominant solution, the math kept offering multiple plausible histories, none clearly better than the others. That's not supposed to happen. Gravitational physics is unforgivingly precise. Given enough information, it corners you. If it doesn't, something is missing. Either the measurements are wrong, or the forces acting on the object aren't fully accounted for. Naturally, scientists leaned hard on the first option. They scrutinized astrometry for systematic errors. They checked timing offsets between observatories. They compared star catalogs, recalibrated reference frames, reran reductions with alternative algorithms. This is the unglamorous grind of astronomy, the part that kills most anomalies before they ever see daylight. 3I Atlas survived the grind. Independent datasets processed by different teams all pointed to the same uncomfortable conclusion. The trajectory problem wasn't a bookkeeping mistake, it was baked into the object's behavior. The next line of defense was non-gravitational forces. Comets, after all, cheat. As ice sublimates, jets of gas act like thrusters, nudging trajectories off their purely gravitational paths. This is well understood and routinely modeled. If 3I Atlas were outgassing in a complex or asymmetric way, that could smear out trajectory reconstructions and explain the divergent solutions. The trouble was scale. To account for the observed deviations, the non-gravitational acceleration had to be tuned very carefully. Strong enough to matter, subtle enough to avoid obvious signatures. And even then, it didn't fully solve the problem. It helped in some windows and made things worse in others. The corrections behaved inconsistently over time, as if the object couldn't decide how it wanted to be pushed. That inconsistency became the heart of the issue. When scientists plotted residuals, how far observations deviated from predicted positions, they expected a pattern. Noise has texture, outgassing has rhythm, rotation imposes periodicity. What they saw instead was something messier, not random but not cleanly structured either. The deviations clustered, then dispersed, then clustered again. It was enough to break confidence in backward integrations. If you can't trust how the object responds to forces now, you can't reliably say where it was before. Some researchers tried a different angle. Instead of asking where 3I Atlas came from, they asked what kind of object would behave this way. The trajectory problem stopped being a navigation issue and became a physical one. That's where things got tricky. Standard interstellar object models assume bodies ejected during planet formation, debris flung out by giant planets, fragments of disks, icy leftovers from chaotic early systems. Those processes produce a distribution of sizes, shapes, and compositions. But they don't usually produce trajectory headaches. Once ejected, the objects coast. They don't carry complicated force histories with them. 3I Atlas seemed to violate that expectation. Its path through the solar system hinted at subtle, changing influences that couldn't be easily reduced to one mechanism. Radiation pressure alone didn't cut it unless the object had an unusually low mass-to-area ratio. Outgassing alone didn't cut it unless the activity was oddly selective and time variable. Rotation-coupled effects helped in some models and broke others. Each fix introduced a new problem. That's when dismissal started to feel less confident. Not publicly, official statements stayed careful, but internally, the trajectory problem became a recurring agenda item. Not because it was dramatic, but because it was stubborn. It kept resisting closure. Then came the comparisons. When researchers overlaid 3I Atlas's behavior with previous interstellar visitors, patterns emerged that were uncomfortable but hard to ignore. Not identical patterns, nature rarely repeats itself exactly, but thematic ones. Slight accelerations, shape inferences that lean toward elongation, rotational complexities that complicated force modeling. It wasn't that 3I Atlas was unprecedented. It was that it seemed to be part of a pattern that was only now becoming visible. And patterns are dangerous. 1 anomaly is noise. 2 is coincidence. 3 is when people start asking whether the underlying assumptions are wrong. The most frustrating part of the trajectory problem is that it doesn't fail loudly. There's no dramatic contradiction, no single equation that explodes. Instead, everything almost works. The models miss by just enough to erode confidence without providing a clear alternative. That kind of failure is the hardest to deal with scientifically. It doesn't tell you what to fix. It only tells you that something is off. As more time passed, the window for observation began to close. 3I Atlas was leaving. Opportunities for new data thinned out. Whatever questions remained would have to be answered indirectly through analysis rather than fresh measurements. That urgency sharpened attention. Revised dynamical models grew more sophisticated, incorporating coupled effects that are usually second order at best. Researchers explored scenarios that would have seemed excessive for a normal object. Most didn't fully resolve the issue. Some improved fits locally, while degrading them globally. And then once again, the object did what it had done before. A late-stage analysis, using the most refined data available, confirmed that no single static force model could reproduce the full observed trajectory. The deviations changed character over time. Not randomly, but not predictably either. The conclusion wasn't sensational. It was understated to the point of being almost boring. The trajectory of 3I Atlas cannot be uniquely reconstructed under standard assumptions. That sentence carries more weight than it looks like. It doesn't mean physics is broken. It doesn't mean something impossible happened. It means the object sits at the edge of what current models comfortably handle. It exposes gaps, not massive ones, but real ones, in how interstellar bodies are expected to behave when they interact with a stellar environment like ours. Scientists don't like unsolved trajectory problems. Orbits are supposed to be the clean part. When even that gets messy, it forces a re-evaluation of confidence. Maybe future observations will reveal that 3I Atlas was just an outlier, a statistical fluke that happened to push models to their limits. Or maybe it will turn out to be an early warning, a hint that interstellar space is delivering objects shaped by processes we haven't fully internalized yet. Either way, the trajectory problem matters. Not because it invites wild speculation, but because it demonstrates how fragile our sense of understanding can be. One object, moving on a slightly uncooperative path, was enough to stall confident explanations across multiple teams. The real breakdown isn't in the math. It's in the assumption that every visitor will behave in ways we already recognize. 3I Atlas didn't crash the system. It just refused to fit neatly inside it. And sometimes that's more unsettling than outright failure.